Evening, everybody. 5 o'clock and it's Tuesday, so time for some Calc 3. This week, we are going to be finishing up Chapter 14 from the book, or Module 4, however you want to describe it. Interesting section today with integrals in cylindrical and spherical coordinates. So we're going to take a look at that. I'll talk about it a little bit. I want to do a couple of examples to really try and help make it a little more concrete. And then depending on how long that takes, maybe we'll spend a little bit of time later, depending on how much time we have left, break into groups, let you guys try a couple from the worksheet, just to start to get the feel for it. Thursday, we're going to do a section called the Jacobian, which I don't want to talk about it too much. You'll see it on Thursday. It's actually one of our shorter sections. So what we might do on Thursday is, if we don't have much time to work in groups today on 14.7, we might work in groups a little bit on 14.7 again on Thursday. Because like I said, 14.8 is a shorter section compared to some of the other stuff we've done, like triple integrals and now integrals in cylindrical and spherical coordinates. We will be finishing this module this week. That means the module quiz is going to be on the horizon, so make sure to keep an eye out for that and prepare for that as it comes up. All right, let's get into this. So last time we did triple integrals. We talked about triple integrals as volume, talked about some of their applications, and mostly we focused on how to set them up. Now what we're going to do is similar to what we did with double integrals. We learned double integrals, then we saw how to do double integrals in polar. That can make some integrals easier. Now we've learned how to do triple integrals. Now we're going to learn about cylindrical and spherical coordinates, which can make some of our triple integrals easier. Not always, but sometimes. So let's talk about the two coordinate systems. We have seen them before. If you can remember all the way back to module 2, we talked about converting from cylindrical to spherical coordinates, some of the equations. So I'm just going to review that real briefly, and then we're going to dive into a couple of examples. So we were doing it over the XY plane. Sorry, not in polar coordinates. That's actually from a week before that. So what we have first is our cylindrical coordinates, which are polar coordinates plus the z-axis. So really, cylindrical coordinates are polar coordinates in 3 dimensions. And the z-axis in cylindrical is same as the z-axis in rectangular. So when we'd use cylindrical coordinates is very similar to when we would use polar coordinates for a double integral. And we'll talk about those here in a second. So instead of a point being at x, y, z, it's at r theta in the xy plane, and then z in the z direction. So our conversions are the same as before. X is r cosine theta, y is r sine theta. I don't have the other conversions on this particular slide, but if you remember, r squared equals x squared plus y squared, and tangent of theta equals y over x. Okay, so all those transformations from polar are the exact same as cylindrical. Again, all we're really doing is adding in the z coordinate, or the z component, to make it for 3D. So here's what we need to think about then. And we did this back in module 2, so I won't spend as much time on it this time. But we have our fundamental surfaces. And we went through these. If r is a constant, that means our distance from the origin in the xy plane is constant. We get a circle. If theta is constant, what we get is a plane. Again, this is kind of going back to module 2, but what we get is a plane in 3 space, actually pretty similar to what this plane here would be. if we actually filled that in and thought about that as a plane, that makes an angle theta. So it's a plane that's perpendicular to the XY plane and parallel and goes through the Z, parallel to and goes through the Z axis. Okay. So that's if theta were set to a constant. Lastly, if Z is set to a constant, well, we get a plane that is parallel to the XY plane. Again, we went back through that back in module 2, so I'm going through it a little quicker this time. I want to focus more on the integrals. But the reason we do these fundamental surfaces is if these fundamental surfaces tend to be our boundaries, that's our hint that we'd want to use cylindrical coordinates. You can also kind of get it from the name, right? If we're looking at a cylinder, then we might want to use cylindrical coordinates. If we're looking at a plane that goes through the Z axis and is parallel to the XY plane, we might want to use cylindrical coordinates. All right. The last one, that does, if Z is a constant, that still could be rectangular. It depends on what our region looks like in the XY plane. But again, cylindrical, we're going to be pretty familiar with because it is very much like polar plus the Z coordinate. So those fundamental surfaces is how we would decide. And we'll, like I said, we're going to look at a couple examples. We're going to do both examples in all 3 coordinate systems and then talk about, what makes most sense. Now, in cylindrical coordinates, we have to think about integrating. And the reason that's important, if you remember from polar, the dA, we had to put an extra R in the integrand. Well, because cylindrical is just an extension of polar, that is still going to be in our integrand. I'm not going to worry about how we solved it, but very similar, we still have to put that R in our DA. And then the order here will depend on what order we want to integrate in. So just like you had to put the R in the integrand in polar, we have to do it in cylindrical. Again, I see cylindrical and polar as the same thing, just cylindrical is the 3D version of polar. We're not going to go to the worksheet just yet. We're going to do the worksheet all at once. We're going to talk about spherical next. So spherical also was something we looked at in module 2. I know the transformations look a bit nasty, but again, it's not something we have to memorize. It really is all right angle trig as far as y, x is rho sine phi cosine theta, y is rho sine phi sine theta, and z is rho cosine phi. Rho is the distance from the origin to the edge of our surface. So it's actually like having a sphere, hence the transformation is rho squared equals x squared plus y squared plus z squared, which is the formula for a sphere centered at the origin with a radius of rho. And phi we let be between 0 and pi. Why is that? Well, 0 to pi would take us down here to the negative z axis. Then to create the sphere, we go from 0 to 2 pi around in theta. So we normally just do phi from 0 to pi so that we don't double count anything when we rotate around with theta. So that's the big reason for the bounds on phi. Usually doesn't end up being too much of an issue. Now, again, this is something we saw before. The order would go, so that's a good question. So the order that we would list a point in spherical typically would go rho. Oh, no. Gosh, I haven't seen a point in, I'm trying to remember now. It should be rho phi theta? I'll double check that, Cooper. That's a good question. When you guys are working on problems, I'll double check that and we'll talk about it. But I think it's rho phi theta. I'm going off the top of my head and I don't have it written down. So good question. We'll get back to that one. All right. So spherical coordinates, let's talk about our fundamental surfaces. If rho is a constant, we get a sphere. Hence the name spherical coordinates. If theta is a constant, we get the exact same thing we do with polar. Okay, and that's that plane. So if we thought of this as making up our plane here, that goes through the z-axis and is perpendicular to the xy plane. So same plane as in polar, or cylindrical, I should say. And if phi is a constant, so this is kind of a cool one. Let's go back to our picture here. If phi ends up being constant, and then we rotate this around, you can see we get kind of a cone shape. So when phi is a constant, we get a cone. So we have a sphere, a plane through the z-axis, and a cone. Those are our fundamental surfaces for spherical, which again tells us whether or not we would want to use spherical if those happen to be some of our surfaces. We're going to look at a couple examples here in a minute where, you know, one of them is really, you know, where maybe it's not so obvious, like it's a combination of them and we have to figure it out. All right. So again, we want to know which to use when. And so that's why we pay attention to the fundamental surfaces. All right, integrating in spherical coordinates. So you saw this in the video, but I don't think the video for today talked about where this came from. So there's a volume element in spherical coordinates, and you saw it in the video. You have to add a rho squared sine phi. Now, Thursday, when we cover the Jacobian, you'll actually calculate, this will actually be calculated where the rho squared sine phi comes from analytically in the video lessons. So I'm not going to do that today, but I'm going to give you a geometric sense of where this comes from before we go to the worksheet. So when we're in spherical and we break this volume up, we break it into a bunch of little rectangular cube shapes here. So this represents our dV. Let me get a pen so I can mark this up a little. So that's our dV, is that cube shape here. And here it is magnified a little bit. Now, what's happening with this, you know, where everything comes from? Well, the d rho is kind of simple because rho is the distance from the origin. So this is just our change in rho. So that's the delta rho right there. Okay, that's that delta rho. Now, this black line and this green line are actually arcs. And to get the arc length, what you do is you multiply the angle by the radius. So let's see how that works out. And that's where these side views come in. So if we wanted to look at this arc length here, why is it rho delta phi? Well, the angle there is delta phi. Rho is the distance or the radius from the origin. So the arc length here, it's blue here, but it's black in this drawing. So just to kind of show you, when they're talking about this one here, that's the same as this arc length here. Guys, this isn't something you have to memorize at all. You just need to know to put the rho squared sine phi in your integrand. I just want to give you a geometric sense of where it comes from. So that arc is rho times the angle, which is delta phi. So that's where that comes from. So we talked about this guy and this guy. Now let's talk about the green. That's this arc length. Now its angle is in the XY plane. So now we're looking straight down the z-axis. So delta theta is the angle, and the distance here is actually rho sine of phi. All right, this comes from right angle trig. Here's phi right here. Our hypotenuse is rho sine of phi. Okay, so that's where that one is coming from. And so this is the radius times the angle for that arc length. Putting those all together give us the delta V, excuse me, for spherical. What do I want you guys to take from this? The biggest part is whenever we're converting to spherical, we need to add in a rho squared sine phi, not theta, but phi, to our integrand, no matter what it is. So like even if we were doing volume of a sphere, we need to have this in there. Now, it's actually not that bad to integrate because rho and phi are separate variables, and rho squared is easy to integrate, sine phi is easy to integrate. Now, depending on what our function is, that could be cleaner or messier, but that needs to be put in our integrand if we're going to convert into spherical. Now, as I was saying earlier, Thursday, and you're going to see in the video lesson that we can actually do it analytically using the Jacobian, which is specifically for changing the system of integration. So in our case, if we were changing from rectangular to spherical, the Jacobian would calculate this piece for us. All right. For right now, for our purposes today, we're just going to realize, hey, we need to have that rho squared sine phi if we convert. And like I said, we're going to do a couple different examples to get a little bit of practice, and we're going to do them in multiple coordinate systems. Now, before I go on to the examples, any questions so far? Besides Cooper's question, which, like I said, I'll double check that, make sure I got the right order because I'm not remembering it at the moment. But I'll come back to that one. All right, let's look at some examples from the worksheet. So this is the worksheet you guys are going to be doing today. Let me put it in chat so you, in case you don't already have a copy. All right, we're going to do 5 and 6 together. 5 is a nice one, and it's a nice introductory one. 6 is a little bit tougher one, which is why we're going to do that one together, because I think some good questions will come out of 5 and 6. Rho theta phi for the order. Okay. Yeah, it's been a while since I've written a point in spherical, so got those backwards. Okay, sorry, I didn't send the worksheet to everybody. There you go. There's the worksheet. Cooper, thanks for checking that out. Rho theta phi. All right. All right, number 5. Let's talk about this one. All right, an ice cream cone can be modeled by the region bounded by a hemisphere of square root of 8 minus x squared minus y squared, and the cone square root of x squared plus y squared. And we want to find the volume. So I've already plotted this one in Calc plot 3D. And all that's going to tell us is, hey, okay, here's a sphere on top. Here's a cone on bottom. And so what we're going to do is we're going to do this in multiple coordinate systems. And what I see when I see this one, I see, okay, well, look at that. I've got a definite top of the hemisphere and a definite bottom of the cone. So I'm probably either going to do rectangular or cylindrical first, because I got a definite top and a definite bottom. So the boundaries or the limits on Z to me are really obvious. Here's my upper Z is the hemisphere. My lower Z is the cone. Okay. So I'll be bringing that back over. I'm going to do a side view of what we got going on. We've got the cone and then the hemisphere. Whoa, that's not coming out good at all. And then the hemisphere on top. All right. So like I said, I see a very clear top Z and a lower Z. So upper bound, lower bound. I'm going to probably do this one in rectangular first, although we'll see real quick we wouldn't want to do that by hand, and we'll switch it over to cylindrical. So the lower bound is the cone. So that's coming from square root of x squared plus y squared. And remember, if you're not sure which surface is which in Calc Plot 3D, you can always turn them on and off to say, okay, that one's making the cone. Upper boundary is square root of 8 minus x squared minus y squared. And we're just doing volume, so dz. I'm going to go ahead and do rectangular, and then we'll switch it into cylindrical. But I think we're going to see real quick that the argument for cylindrical is pretty strong, because this is where we need the shadow region in the xy plane. Now, I know there's these extra pieces here, but that's just because it's hard to cut off in the drawing. But there's a circle here. That's my shadow region in the xy plane. So let's do, so what we need is what that circle is. Well, notice what that circle is. It's formed by the intersection of the two curves. So we're going to, that happened, I think, last time as well. So we need that intersection. How are we going to get that intersection? Both of these are equal to z. So we're going to set them equal to each other. So that intersection curve is going to come from having square root of 8 minus x squared minus y squared equal to square root of x squared plus y squared. Okay. What we're looking at is we're looking at that shadow region in the xy plane. It is some circle centered at the origin. We need an equation for that circle. That's going to come from solving this. Let's make sure we have enough room there. All right, so first thing we would do in solving this, let's go ahead and square both sides, get rid of those radicals. So we end up with 8 minus x squared minus y squared equals x squared plus y squared. And we'll add the x squared and y squared over to this side. So that's going to give me 8 equals 2x squared plus 2y squared. And then we'll divide everything by 2. Sorry about writing on top of our circle. But we get the equation for the circle here. 4 equals x squared plus y squared, which we know is a circle of radius 2. All right, remember that this is the radius squared in both our circle and spherical formula. So, guys, this is something by now you should be getting fairly comfortable with, is how to do the bounds for a circle. So if it's a circle of radius 2, it doesn't matter which variable we do next. But we want to solve this for y if we want to do y next. So y would be the plus and minus square root of 4 minus x squared. The minus gives our lower limit. The plus gives our upper limit. And then we're doing y next. Lastly, we got our x, which goes from one end of the circle to the other. So -2 to 2. So there is going to give this guy, once we throw the dx on there, will give us our volume in terms of rectangular. Questions about that setup? just like with the last class, I am more focused today on setting these up than I am solving them. So when you are working in groups, feel free to use Symbolab or Wolfram Alpha to calculate the value. I want you focused on setting them up. All right, let's go. Let's do this exact same one. I'm not even going to leave this page. We're going to do a different coordinate system. Okay, let's do blue. We are going to do cylindrical. Now, first off, we need to convert these so that they're in cylindrical. So as a reminder, for cylindrical, r squared equals x squared plus y squared. That means r is the square root of x squared plus y squared. So this lower limit actually is just r. Up here, not going to simplify quite as nicely, but we can factor a negative out of this. I'm going to write it here in blue just so you can kind of see what I'm doing for the substitution. I'm going to rewrite this upper limit as the quantity x squared plus y squared, which, like we just said, is r squared. So that upper limit is square root of 8 minus r squared. Now we're doing cylindrical, so we need to put an r in there, and we're still doing z first. That's one of the nice things about going from rectangular to cylindrical. Z is the same, so if you're doing z first in rectangular, you might as well do it first in cylindrical. Now here's where cylindrical is going to give us a distinct advantage. This is a circle with a radius of 2. Much easier to do in cylindrical coordinates. So in cylindrical, we are going to have r is going to go from 0 to 2. That'll take care of the radius. And then we'll go around this circle from 0 to 2 pi in theta. Because both of these last two sets of limits were both constants, the order here can go either way. We could have done d theta dr or dr d theta. Out of habit, I tend to do dr before d theta. This will give us the exact same volume as the integral above, except now we're in cylindrical. We can see the blue integral, like if we had to do this one by hand, the blue integral is going to be much easier than the black integral. So cylindrical would be a better choice for this one. Okay, questions about the cylindrical version? The nice thing about cylindrical, we already had some practice at that when we did polar. So those guys are equal. All right, let's move to spherical. Now, guys, remember we talked about the fundamental surfaces. A sphere is a fundamental surface of spherical, and a cone is a fundamental surface of spherical. So chances are this one in spherical may actually be even easier than cylindrical. Let's see how that works. All right. So first thing we have to deal with is I think it's going to be easiest to do rho first. Rho goes from the origin up to the edge of our sphere. So that's going to be rho there. So rho is going to go up from 0 up to the edge of our sphere. So we need the radius of our sphere for that upper limit on rho. So rho is going to go from 0 up to the radius of our sphere. Well, this is the formula of our sphere. If we want to put it in the standard formula of our sphere, we could square both sides and put the x squared and the y squared on the other side. And we would get x squared plus y squared plus z squared equals 8, which is a sphere of radius radical 8. Remember, this is r squared, just the radius squared, just like with the formula of a circle. So rad 8 we're doing spherical, so we do have to put in a rho squared sine of phi, and we're doing rho first. All right, so that takes care of our first set of limits. Now the next one, let's do phi next. All right, let's talk about how phi works because we don't have a lot of experience with it. So what phi does is it measures from the positive z-axis. So let's put in a positive z-axis there into our cone. So there's the positive z-axis, and it measures in the counterclockwise direction. Now, because our formula is z equals square root of x squared plus y squared, if we're looking at a trace, so actually let me actually go one step further and put a horizontal axis in here. If we're looking, let's say that this is, for argument's sake, let's say this is the xz plane, then y would be 0. And so z would equal the square root of x squared, or this line here, right here, would be the equation z equals x. Now, why is that important? Well, that means that this is our 45-degree angle, or our angle of pi over 4. By knowing that trace in the xz plane or the yz plane, we would have gotten the same exact thing. We need that angle because phi is going to go from 0 out to pi over 4. That's what phi is. I know my drawing is getting a little messy here. I apologize for that. But phi is going to go from 0 to pi over 4. So what's happening is you have rho, which goes from 0 up to the edge of the sphere. Then phi rotates out to the side of the cone. That's how those two are working in conjunction. So that's why our limits on phi are going to be 0 to pi over 4. Okay. So we did phi next. So again, rho took us from 0 up to the edge of the sphere. Phi rotated us over to the side of the cone. Now theta is going to rotate us around the z-axis to get that three-dimensional cone. So theta will be 0 to 2 pi. Notice in this integral, all of our limits are constants. So we could do this in any order we want. Also, even though we had to put a rho squared sine of phi, this is actually a pretty easy one to do by hand because it's easy to do the antiderivative of rho squared, and it's easy to do the antiderivative of sine phi. Depending on how much time we have at the end, we might come back and look at doing this one by hand just for some practice, or maybe we'll look at it Thursday. But like I said, I want to focus more today on setting these up than calculating. Guys, all three of these will give us the same volume of this ice cream cone. And I think you can kind of see they get a little bit easier as we move from rectangular to cylindrical to spherical. And again, it's all because of our fundamental surfaces. We only had one fundamental surface in terms of, so our fundamental surface in terms of cylindrical would have been when we look straight down our graph, we get that circle, right? So that would be the cylinder cutting out this image here. But because we have the sphere on top, that's not a fundamental surface for cylindrical. That's why we have one of our these outer limits, not outer, I don't want to call them outer, sorry. The limits on Z are still in terms of R. Because a cone and a sphere are fundamental surfaces of spherical, all of our limits end up being constants. So this is going to be which one is going to be easiest if we had to do them by hand. All right, questions about this one, about spherical, cylindrical, rectangular. Number 5. All right. Good, good, good. I'm glad that this is a good one to start with, right? I'm going to have all you guys in your groups do number 1, which is somewhat similar. And then after that, maybe try one of the other ones. I'm going to let you guys kind of pick and choose after you try number 1. All right, let's go on to number 6 because things get a little bit more interesting. And we're going to do the same approach. I might not start with, maybe I will start with rectangle. Actually, I will start with rectangle. I'm just going to keep the same order. And then we'll talk about which is easier and why. All right, so 6. Now we actually have a function we're integrating over. And then we have a region which is outside the cylinder, x squared plus y squared equals 1, and inside the sphere of radius rad 2. So we're kind of stuck in between. We have one surface that's a cylinder, which is a fundamental surface of cylindrical. And then we have one fundamental surface, one surface that's a sphere, which is of spherical. So we're kind of caught in between. Rectangular is actually going to be the messiest on this one. And I do want to look at it because something interesting happens there. But here's our plot. It's hard to see exactly what's going on in this plot. So I'm going to make our sphere a little bit more transparent. So our region is this volume that is between the sphere and the cylinder. I'm not worried about the top. If it's in the cylinder, it's automatically cut out. So if you took a tennis ball and you cut through it with a cylinder, what you got left would be our volume. I guess maybe not a tennis ball is not the best example since it's not solid. How about a racquetball? If you took a racquetball and drilled through it, what you have left is what our region is, okay? So let's see how we're going to handle this guy. And let's talk about it in rectangular first. So rectangular, rectangular is an interesting one in this one. And the reason rectangular is interesting is because of the nature of the shape. Notice it's spherical on the edges, but not inside the cylinder. So there's no way to do this with a single integral. So what we're going to do is we're going to integrate the function over the sphere, and then we're actually going to subtract out that part that is inside the cylinder. So it's going to be done with 2 integrals. So we're going to do everything inside the sphere over our function. And then we're actually going to subtract out this part that, we would remove if we were running through it with a drill. So I just want to give you the motivation for what we're doing here. So the nice thing is the sphere itself, integrating over the sphere is actually not that bad to set up. So our sphere is x squared plus y squared plus z squared equals 2. So, let's say we want to do z first, which I think is going to be easiest because we have to do inside there. Z is going to be square root of 2 minus x squared minus y squared, plus or minus, because we are doing the whole sphere. Right. So what I'm doing right now is I'm kind of pretending like this doesn't even exist. I'm just going to set up the integral for our function over a sphere in rectangular. And it's not pretty. All right. So first off, z is going to go from negative square root of 2 minus x squared minus y squared up to positive square root of 2 minus x squared minus y squared. And guys, what I'm doing here, this would be how you'd set up for any sphere in rectangular. Now we are integrating over the function x squared plus y squared, and we just said we're doing z first. Okay, now the nice thing about doing a sphere in rectangular is if you can set up one set, you can set them all up, because if we take this thing and we look directly down the z-axis, what we get is a circle of square root of radius square root 2. All right, we know the formula for that is basically this formula with z set to 0. So it's x squared plus y squared equals 2. Again, guys, you're going to get really used to doing spheres and circles in rectangulars. And so as messy as it looks, we do it so many times. Let's do y next again, just out of habit. So negative square root 2 minus x squared to square root 2 minus x squared. How did I get those? Solve this for y. Y equals plus or minus square root of 2 minus x squared. So that's our limits on y. Our limits on x are the radius. So negative rad 2 to rad 2. So what that's going to do is that's going to calculate that function over this sphere. Now what we're going to do is we're going to remove the center, or remove the part that we would by drilling through it. Okay. Now we got to think about what this looks like. So what I want to do, so you can kind of see it on here, I need to increase the transparency of our sphere a little bit. But I'm also going to increase the transparency of our cylinder a little bit, but not quite as much, because I want you to see what's happening. We look at this directly from the side. Notice I've got a little sphere top here, then straight down, sphere bottom here, and then straight back up. So we've got basically a cylinder with a rounded, with a spherical, with a circular top and a circular bottom. Okay.
Professor?
Yes.
So for the d, or I guess it's the dx at the end, why don't we have the square root of 2 minus y squared?
There's a couple of reasons for that. Number one is we can't have it. Our outside limits have to be constants, because otherwise we won't get a numerical value for our result. The other reason, though, in terms of what's going on, let's bring our circle back up. And this is anytime we're doing a circle, it's always going to be the same basic idea. So we're integrating over this circle. What's happening is, if we think of it in terms of area, the top is square root, we did square root of 2 minus x squared. Bottom is square root of 2 minus y squared. So that's going to take care of the curvature. And then in x, all we have to do is go from negative rad 2 to rad 2. So we've already taken care of the circular shape in our limits on y. We don't have to do it again on x.
So you could have done it the other way too?
Absolutely. 100%,
okay.
Garrett, 100%.
Thank you.
Yeah, no problem. That's a good question. Okay, so we got kind of this pill shape in 3D that we have to figure out now. And remember what we're doing. We're subtracting this out. I'm not going to get them on the same line. This is a subtraction sign. We're doing the whole thing, and now we're subtracting out what's inside. Now, we're still going to have the same function inside, so x squared plus y squared. Now, here's what's kind of nice. Notice that this is the bottom of the sphere, and this is the top of the sphere. So our inside limits actually end up being the exact same inside limits as here, because that's the bottom of our sphere. That's that negative square root of 2 minus x squared minus y squared. And that's the positive part of it. So the z actually isn't too bad. So negative square root of 2 minus x squared minus y squared. Don't really like how that came out. There we go. Up to the top part of the sphere. And now what we have to do is we have to trap it inside that circle. Well, let's bring our drawing back. That's the sphere. We add that cylinder back in. And what that creates right here, and we can see it maybe a little better here, it's basically just going to be a circle of radius 1. Maybe actually, I might say better without the sphere. Let's go right back down the XY plane. If I get rid of the sphere, what we have is, you can kind of see it there, it's because it's at this angle. What we have is a circle of radius 1 in the XY plane. So that's where we have to do these sets of outside limits. So that's basically going to be a circle of radius 1, which is x squared plus y squared equals 1. Not a huge surprise, right? That was our cylinder. To Garrett's point, we can do either set of limits next. So let's switch it just for practice sake. If we wanted to do x next, we'd solve this for x instead of y. So it'd go from negative square root of 1 minus y squared to square root of 1 minus y squared. And then our last set of limits are just going to be our radius, negative 1 to 1. So I know it's a bit messy. It's a bit messy, but
Is this,
oh yeah, sorry, go ahead, Garrett.
is this accounting for the top and the bottom of the sphere?
Yes, they're accounted for right here and here. So so this upper limit is accounting for this piece of the right there. This guy's accounting for this piece. What these outer limits are doing, that's taking us all the way around and filling this in, making this a three-dimensional object.
Okay, we're subtracting this because it's inside the cylinder?
You got it.
Okay.
Yeah, guys, I definitely, we don't do many of these, and I wouldn't recommend doing this one this way. I'm doing this because we haven't done one like this, but just a reminder of what we did. We basically did the whole thing. So if we did this function over a sphere, over this sphere, that would be this top integral. Then what we did is we said, oh, but we got to subtract out the part that we drilled out. And that's what this bottom integral does. So guys, I'm not recommending you guys do this one this way necessarily. You can, obviously, but I wanted you to see why sometimes we need these other systems. This one's going to be much easier to do in cylindrical or spherical than rectangular. Which we're going to do. We're going to do all, like I said, we're going to do this exact same one. We're going to redo it in cylindrical next and then spherical. And we'll talk about which one might be easier. You could probably argue either way. But before I do, other questions about it in rectangular.
Yeah, maybe a quick question. So do you always just start off with rectangular? Is that the only way you can start off on any triple integral, finding the on the regions, or can you go to cylindrical and
yeah, no, good question. You want to use whichever system is going to be easiest, right? So I'm going through the order just for comparative purposes, but let's go back to the first one. This one, again, we would recognize that we have a sphere and a cone, which are both fundamental surfaces of spherical. So ideally, we would have gone right to spherical or right to the purple one. The one we're working on now, because one fundamental surface, one is a spherical fundamental surface and one is a cylindrical fundamental surface. We would have gone either to cylindrical or spherical first, not rectangular. Rectangular is not the one we would have done first.
Oh, okay. Gotcha.
So you want to do whatever's best for you. Because remember what our end goal, the end goal isn't to write these in all three systems. The end goal is to get the value of the definite integral. So we want to do that in whatever way is going to be easiest for us. And that's going to, that's going to depend on the user a lot of times. I always do kind of think of them in rectangular first, but that doesn't mean I would necessarily on paper do it in rectangular first, because I'm going to explore those fundamental surfaces. That's a good question. Yeah, I don't want you to think, guys, that I'm doing this because I want to do each one, but in practice, like if we were doing 6, I would have done probably cylindrical first and spherical that next, and then compared the two to see which one's going to work out easier. Okay, time for another coordinate system. So let's look at what we got going on in spherical. So we've seen the image. What I'm going to do is do my best to draw this so we can kind of see what's going on. So we've got the sphere, and then we've got this cylinder that's actually kind of removing that part of the sphere. Okay. So this one actually works out fairly nice in cylindrical because one of our surfaces is a cylinder. But we do have to think about the Z, what's going on there. And that's where we could actually steal from rectangular. Z went from the bottom of the sphere to the top of the sphere. We're going to do the same Z in cylindrical. The only difference is we're going to do it in cylindrical, not in terms of x squared and y squared. So this upper limit will be 2 minus r squared, and lower will be negative, square root of 2 minus r squared, negative square root of 2 minus r squared. Okay, so basically we're doing the same limits for the z, except we're doing them in cylindrical. So we get to substitute the x squared plus y squared with an r squared. All right, so we're doing z first. We're in cylindrical, so we do have to add an r to our integrand. And we also need to write the function in cylindrical, which actually works out pretty nice for us because x squared plus y squared equals r squared. So that's where that r squared's coming from. That's our function there. That's it. Let's make that look like more of an r instead of a v. Okay. And what we'll do in the next step, we'll multiply those together. But for notes purposes, I want you to remember where they came from. That was the x squared plus y squared. This is the one that goes along with our dv. Now, here's where it's going to get much nicer than than rectangular. If I were to look straight down this thing, I've got my sphere on the outside, and then I've got my cylinder on the inside. So what we need is the spot in between them. So we need the radius of both of these. Now we know the radius of our cylinder is r equals 1. Didn't come up very nice. R equals 1. And the radius of our sphere is r equals rad 2. So r is going to go out from 1 to rad 2 because we want to eliminate the center. And this is why this one only needs one integral. It was able to be handled with the radius, with r. So those are our limits on r. Lastly, we need to take this thing around the XY plane, and that's going to be done by theta. So 0 to 2 pi. So significantly nicer than what we were looking at in rectangular. You know, we're going to get a bit of a mess here, but we'll get an even power, which might work out nicely with those square roots if we had to do it, which should work out nicely with those square roots if we have to do it by hand. But much better than having to deal with two integrals. That is questions on doing it in cylindrical. All right. Let's see. Yeah, we'll do spherical on here, so we can kind of for comparative purposes. All right. So now we like spherical because one of our surfaces is a sphere, which is great, but we do have a bit of an issue, right? Because this part here is a sphere. Oh, sorry, guys. I hadn't seen the questions in chat. Okay, so hang on. Before we go on to spherical, one question. Did we change the 1 from x squared to y squared? No. So make sure we differentiate. X squared plus y squared equals 1 created the cylinder. That's different than the x squared plus y squared that we're integrating over. This is just our transformation from cylindrical. X squared plus y squared equals r squared. That's different than this. Now, where did that show up? Well, right here, because before we had to deal with that circle x squared plus y squared equals 1. Well, now because x squared plus y squared is basically our r squared, we have an r of 1 for the radius of this cylinder. And yes, the other question, yes, in rectangular, we needed 2. There's no way to do this in rectangular with a single integral. Cylindrical allows us to do it with a single integral, and so will spherical. And the reason is because one of the regions is a sphere, hence spherical, and one of the regions is a cylinder, hence cylindrical. Because those coordinate systems are designed for those kind of shapes, it makes them much easier to deal with. Sorry, guys, I missed the questions in chat, so feel free. If I miss your question, obviously don't hesitate to turn on your mic. I'll try and be better about keeping an eye on those. Other questions before we go into spherical? All right, so let's talk about spherical. Now, the nice thing about spherical is our outer limit is a sphere. The thing that'll make it a little tricky is right here. Our inner limit on rho is not a sphere. It's actually part of this cylinder. So while, because we have to cut out this center, rho, which normally goes from the origin, see if I can do this a little bit better, is really just going from the cylinder out to the sphere. All right, it just kind of goes from here to here, from here to here. And notice what that does. That means while our upper limit will be constant, our lower limit's going to vary because rho isn't always the same distance at every point. So this one gets a little bit interesting, but here's what we can do. We have a formula for that cylinder, right? We know that the cylinder is x squared plus y squared equals 1. So we're going to use our transformations. So let me bring those up. I'll bring the worksheet back up here in a second. We're going to use our transformations for x and y. Let's go back to that sheet right here. And we're going to rewrite this equation in terms of spherical coordinates. So x is going to be rho sine phi cosine theta squared plus rho sine phi sine theta squared equals 1. All right. That means now I can square everything. Now I'm going to have rho sine phi squared, and I'm leaving this in parentheses on purpose. You'll see why here in a second. Cosine squared theta. We could write it as rho squared sine squared phi, but we'd end up undoing it later. It's not a big deal, but because I know where we're heading on this one, I'm kind of going a step ahead. And this one, rho sine phi squared sine squared theta equals 1. Now, what's nice about this is I can factor out the rho sine phi squared. So rho sine phi squared, and look at what's left. Cosine squared theta plus sine squared theta equals 1. And we know from our Pythagorean identity, sine squared plus cosine squared equals 1. So we end up with rho sine phi squared equals 1, which we can take the square root of both sides. We don't need to account for the positive and negative because we'll take care of the negative side with our phi and our theta. So we end up with rho sine phi equals 1. And remember what we were looking for, a limit on rho. So solving this for rho, I get rho equals 1 over sine phi. That is this limit here, our lower limit on rho. So our lower limit is going to be 1 over sine phi, and then our outer limit is just the radius of our sphere. Square root of 2. Now, we're doing rho first. We also, while we're at it, we need to convert our function into spherical. Now, I'm not going to do this over again. Remember, our function was x squared plus y squared. So right now, I'm just going to, let's just focus on the left-hand side of the equation. X squared plus y squared simplified down to phi sine the quantity squared. All right, so that's rewriting our function in terms of spherical. And then remember, we also need the rho squared. This is just part of our dv, sine of phi. And we did rho first. Okay. I know a lot going on in that first step. So I want to do, I'm going to slow down a little bit. And if you have questions, let me know. But this here, that's our transformation of x squared plus y squared. This here is that part of our dv, okay? Just so you know where this stuff's coming from. The lower limit, well, the lower limit for rho is the cylinder, which means we need to rewrite the cylinder in spherical. That's what we did here in this part. So this is rewriting the cylinder in spherical. I apologize for my handwriting. It is not good today. So that's our inside limits. All right. Questions about those before we go on to other limits? All right, let's talk about phi next. We could really do either next, but phi is the more interesting one. Theta is going to be 0 to 2 pi. We already kind of know that. But I want to talk about phi. Remember that we only want this part of the sphere that's in purple. So I've got bounds on phi that are going to go from here. Now we'll do them in black. That actually, I think that makes it easier to see. To here. Oops. All right, so we need to look at where those things intersect. So we have to figure out basically, phi's lower limit is going to be this angle here. Phi's upper limit is going to be this angle here. Now my drawing is getting just a little too messy. So let's come down here and talk about phi. Cooper, we only need one integral? Oh, sorry. No. We're doing the next set of limits now. Yeah. It's going to be a triple integral. Sorry about that. I didn't write the integration symbols out front like I had been. All right. So here's that cylinder sitting inside the sphere. And what we need is this angle. Now, we know with the symmetry, that angle is going to be the same as the angle down here. So if we can find this one, we're in good shape. So let's think about how we can find that. Now, let's think about what we know in this triangle, because we do have a right triangle here. We know that this side is 1 because that's the radius of our cylinder. We know this side is rad 2 because that's the radius of our sphere, right? It goes from the center to the edge of our sphere. By the Pythagorean theorem, this side has to be 1. So we've got an isosceles triangle, which means this angle in here has to be pi over 4, which means this angle also has to be pi over 4. Now, so our lower limit on phi is pi over 4. Our upper limit actually has to go from our positive z all the way to this side. So it's pi minus pi over 4. So our lower limit, as we saw, is pi over 4. Upper limit is 3 pi over 4. So how did we get the 45-degree angle? Sorry, my drawing isn't a little bit better. This triangle right here, let's make that a little bigger. So we're zooming in on that triangle. We know that this side goes from the center out to the sphere. So we know this side is rad 2. This side is the radius of our cylinder. So that's 1. And this side has to be 1. So we have a 1, 1. Because this is the radius of the sphere, right? It might be a little easy. Sorry, my drawings aren't better. But where these two intersect is the edge of the sphere. And we're going from the center to the edge. So is everybody seeing where I'm getting the rad 2 for this length here? It's a radius length of our sphere because it's going from the center or the origin to the edge of the sphere. This one we know, this side we know is 1 because it's the radius of the cylinder, which means this side has to be 1. And once we have that, because we know this is 90, we know both these angles have to be 45 degrees or pi over 4. Questions about the limits on phi? for this one, because of the symmetry and a lot of these, on a lot of these guys, you'll find a lot of these, theta is actually one of our easiest ones. Theta is going to go from 0 to 2 pi because we're going all the way around. And once again, you think thinking easiest is cylindrical? If we had, yeah. So let's see. If we clean these up, I think you're going to be right. Although that 1 over sine phi could be interesting. Like if we had to do these by hand, which I'm not asking you to do. You know, this one, we're going to get a rho cubed, which isn't too bad to deal with. Actually, this one might not be bad. Let's, all right. So actually, okay. So before we go on, questions at this point. All right. So, guys, I'm looking at the clock. I don't think I'm not going to break you into groups today just because of time. What we'll do is we'll do groups on Thursday so you can try one of these. Because like I said, 14.8 will be a shorter section. But let's, you know what, let's go ahead and take a look at these and see if, you know, what they look like if we were to have to try and do them by hand. I want to leave this up. So I'm actually going to use a different whiteboard. Here, so that we have our equations still. And let's see what we get for cylindrical first. All right. So for cylindrical, we have 0 to 2 pi. I'm gonna have to write a little bigger since that's so thick. 1 to rad 2, those aren't a problem. It's these inside limits that get a little interesting. Negative square root of 2 minus r squared to square root of 2 minus r squared. And then we have r cubed dr, oh, excuse me, dz, dr, d theta. So if we were dealing with this one, first thing we would do is integrate with respect to z. So let's see what if it gets messy, we won't go too far with it. I don't want to take up the whole rest of our time with this, but because we have a few extra minutes, let's just play around with them just a bit. And this is going to be r to the 4th over 4. No, excuse me, not r to the 4th over 4. What am I thinking? This is going to be r cubed times z. And z is going to go from negative square root of 2 minus r squared to square root of 2 minus r squared. And then we still have to deal with dr and d theta. So plugging those in for z, we're basically going to get this minus the negative of this. So we're basically going to add those two together. So we'll have 0 to 2 pi, 1 to square root of 2, r cubed times the square, times 2. Let's put the 2 out front because we'll be adding those two together. Square root of 2 minus r squared dr d theta. Okay, not the nicest one we've ever had, but doable. So what we would do from here is we do a u sub. So u equals 2 minus r squared.
I have a question.
Oh yeah, sorry, Cooper.
Oh, it's all good. The 2 is because it's, if we actually like put it like all the way out, it'd be root 2 minus r squared minus a negative, right?
You got it.
Okay.
Yep. Yeah, that too. I wanted to put it with this just so it'd be more obvious. But yeah, it's basically we're taking this, we're adding this together with itself. So we have two of them.
Okay, all
I
right.
kind of skipped that step. But
Oh,
yeah,
I was just wondering. Thank you.
yeah, no problem. du is going to be a negative 2r dr, which is nice. We're still going to get left with an r squared. But what we would do is we would manipulate this to solve for r squared. You know, we take that and we solve it for r squared. We get r squared equals 2 minus u. It's not going to be pretty, but it's doable. I think you're right, Ryan. I think this might be the easiest. But we're going to take a look at let's take a look at spherical. We might come back to this. I just don't want to run out of time. I want to take a look at spherical. So, but also I want to make sure you guys are seeing what I'm talking about, because, you know, now what's going to happen is we're going to have 0 to 2 pi in theta, which is great. We're going to change those limits. Now, what's going to happen here? I'm splitting this guy. I do introduce a negative. So we are going to have a negative sign in here. We'll deal with that later. Then we've got a 2. We're going to take one of the r's. We're going to basically split this guy into r and r squared. The r dr is going to be the du. And then the r squared, we're going to substitute in 2 minus u. So what that ends up looking like is 2 minus u times square root of u, which is very, very doable. Du d theta. And our new limits on u, if r is 1, r squared is 1, 2 minus 1 is 1. So that actually stays the same. And then check out what happens with our upper limit. If we put in rad 2 squared is 2, 2 minus 2 is 0. That's actually going to probably fix that negative sign. Actually, let's go ahead and finish this one. We're in good shape here. If you want, one of the things you can do, it's actually pretty cool. If you want to get rid of that negative, you can flip those limits, turn that positive. 0 to 2 pi, 0 to 1. This is u to the 1/2. So we're going to have a 2u to the 1/2 minus u to the 3/2 du d theta. And sorry, I kind of fell down the rabbit hole on this one. All right, now we do our antiderivatives, which won't be too bad. This is going to be 2 times 2/3 u to the 3/2 minus 2/5 u to the 5/2. Those are going from 0 to 1 d theta. And don't worry, guys, I'll be posting this as well. All right. And the nice thing are those limits are easy to work with. Plugging in 1, we just get the coefficients. Plugging in 0, zeros them out. So we end up with 0 to 2 pi. What are we going to have left? 4/3 minus 2/5 d theta. So we'll combine those fractions. So we've got, let's see, we're going to have to make them into 15ths, right? So 20 over 15 minus 6 over 15. So basically we have 0 to 2 pi of 4 over 15 d theta. Integrating here gives us 4/15 theta from 0 to 2 pi. So we're going to get 8 pi over 15. Whew. Sorry about that, guys. I didn't mean to go through the whole thing. I was just going to kind of look and see which was easier. Okay. So this is still good practice. We're you know, it's good to go through solving a couple of these. All right. Now let's just see what this would have looked like. Whoops, I did not mean to do that either. Let's just see what this would have looked like in spherical. Again, you know, our goal is to make it as easy as possible on ourselves. If we're trying to do this one in spherical, we have 1 over sine phi to rad 2. The 4/15, let's see. 4/3 minus 2/5. So it came from combining those fractions. Where did that come from? If we put in our limits here, if we put in 1, we're going to end up with just 4/3 here and minus 2/5. If we put in 0, it's going to 0 out. Did that help where the 4/15 came from? So if we do 4/3, let's just go through this, make sure everything looks good. So we had to do the 4/3 minus 2/5. So every whiteboard works different. Given these a common denominator of 15, we'll get 20 over 15 minus 6 over 15. And now I see what you're asking about, Ryan. I screwed up. Thank you. Should have been 14. Thank you, thank you, thank you. Thank you, thank you. 14. This will be 28. That actually looks better. All right, thank you. Totally missed that, guys. Appreciate you guys checking my math. All right, let's just, here's all we're gonna do. Let's just start this. I just want to see what the beginning of this one looks like. If we can get through the first set of limits, you know, the rest isn't bad because they're all constants. But we got to see what's going to happen with phi on this guy. So we're simplifying this formula. We're going to have a rho squared and a rho squared. So rho to the 4th. Yeah, I think this thing is going to be a little bit messy. And a sine squared phi times another sine phi. So sine cubed phi d rho d phi d theta. Oh, look at that. Made a pretty little phi for us. All right. Let's just see what happens. I'm not going to go too far with this one, but I don't think it's going to be, it might not be too bad. Let's take a look. All right. Very first thing we're going to do is integrate with respect to rho. So rho to the 5th, this is going to be what determines how nice or ugly this one's going to be. 1 over sine phi. Whoa, that time it didn't work out so nice. Rad 2. And then we got our other 2 limits there. We've still got a sine cubed phi, d rho, d phi, d theta. Or sorry, d phi's done. Sorry. Yeah. I can't erase that. Oh boy. We already did d rho. Actually, I erased the wrong one too. Jeez. D phi, d theta. I'm not going to put the limits in right now just for time's sake. I just want to work this one through just so we can kind of see what happens. So when we plug these limits in, we'll put those in later. We're going to have a rad 2 to the 5th over 5 minus 1/5. Here's where it's going to get real messy. 1 over sine phi to the 5th. And then that whole thing is getting multiplied by our sine cubed phi. And then we'll still do a d phi, d theta. So here's where this thing's going to get a little bit messy. We're going to have to distribute the sine cubed phi, which is not going to be pretty. It will cancel out with most of these. Unfortunately, those sine phis end up in the denominator. I'm just going to do one more step on this one, and then I'm going to stop it because it is going to get a little messy, and I'm not going to take any more class time with it. But we'd have red 2 to the 5th over 5 sine cubed phi minus 1/5. We'll have a sine cubed phi over sine to the 5th phi, which we can simplify, d phi d theta. Again, from pi over 4 to 3 pi over 4, and then from 0 to 2 pi. All right, this one won't be, well, no, neither of these are going to be very easy to do because sine cubed is a chain rule. We'll have 1 over sine squared. So yeah, this thing is going to get really messy from here on out to do as a definite integral. So Ryan, you were 100% correct. We definitely want to do this one with cylindrical. Okay, you know, yeah, I'm not even if we had time, I probably wouldn't keep going through with this one just because it's getting to be a little messy. All right, so we only got a few minutes left. I just want to kind of close up a little bit today. We're gonna, yeah, exactly, Andre. We move to technology when needed. So talk a little bit about what we did and what we're going to do on Thursday. So first off, guys, realize this problem that we just worked, this was, oops, where'd the worksheet go? I lost the worksheet. It's around here somewhere. This was number 6 on the worksheet. So I don't want you to think that this is going to be like the problems that you see in the homework. This was a harder problem. You saw how messy it got in rectangular, and even in spherical, it got messy. Even in cylindrical, it wasn't pretty. It just worked out nice. This is a tougher problem. This is like a take-home problem level problem. Because this is something I would want you to use technology on. I don't want you doing a bunch of these by hand. The first problem, this is a little more reasonable for like a homework level problem. Probably a little tougher than what I'd put on the proctored exam. Like I said, with the proctored exam, you know, guys, I want you to realize I'm going to give you very straightforward regions, okay? Meaning it's going to be a sphere or a part of a sphere. It's going to be circular. It'll be much more straightforward on the proctored part of the exam, okay? Because you won't have access to things like the Calc, the 3D plotter. So I just want you to realize that the 2 problems I picked today, I picked them specifically because they were a little bit harder than, you know, what you might see on the beginning, especially at the beginning of the homework, or what you would get on a proctored exam. I wanted you to see one that, you know, was homework level, which is number 5, and then one like number 6 that is a little more difficult. What we're going to do for Thursday, I'm only going to spend a little bit of time talking about 14.8. It's one of our shorter sections. I think once you see the video lessons, you'll have a pretty good handle on it, because it is just finding a Jacobian, which is just basically, it's a lot like doing the cross product. So it's more algebraic heavy than conceptually heavy. What I'm probably going to spend more time on Thursday is triple integrals. Let you guys work on a couple triple integrals in your groups and see what kind of questions come out of that, because that's where I feel like we need the most work from this module. It's the toughest part in this module are the triple integrals. So that's the plan for Thursday. We're at 6:30, but any questions at this point? I'll post the video from today's lesson along with the whiteboards tonight. So if you want to go back through anything we talked about, it'll be up there. So the main things I want you to do for Thursday, make sure you try a few of these, maybe try the first few from the homework and, because you'll have time to ask questions on some of these triple integrals. Because that's the other thing. Thursday, because we're not going to need a lot of time for 14.8, you'll have time to work on problems in groups, or maybe we'll, do a couple questions in whole class together as well. Okay. We'll have a little bit more free time on Thursday. So if you guys don't have any questions, that's what we wanted to get through today. Again, I'll post this stuff tonight. Just a reminder, the take-home problems from this module are already available. We only have one section left, so you can get started on those. And we finish up this module on Thursday, which means the module quiz will be in the near future as well. So you can start preparing for that. Any questions about any of that, about what we're doing Thursday or anything? All right, guys. Yeah, triple integrals take some getting used to. One of the things that I'll tell you guys, this section 14.7 has actually become one of my favorite over time. Probably not when I was a student, but what I find really interesting about this section is all the different ways that you can do the triple integrals. I always like to say, think of solving a math problem like doing a puzzle, right? Some puzzles are tougher than others, depending on how the pieces are cut and the image of the puzzle. Some problems in math are tougher to do. But what we do is we take the pieces and we take our toolkit of solving and we just kind of work through it. I always found this section really cool to see, okay, I was able to do it in cylindrical, but can I do it in spherical? Can I write it up in rectangular? So kind of like number 6, that's kind of what I was doing. Like I said, I wouldn't do this one in rectangular in practice, but because I'd already set it up in cylindrical and spherical, it's all right to set it, to me, it's a challenge. I like the challenge of trying to see if I can make sense of it in rectangular. Oh yeah. Guys, with triple integrals, the book, I call it bookkeeping. It reminds me of like integration by parts. When you have to do integration by parts multiple times on an integral, integration by parts by itself isn't hard, but when you have to do it multiple times, it is so easy to forget a negative, misplace a constant, et cetera, et cetera. Same thing with triple integrals. The bookkeeping, if you're doing them by hand, is very important because we do the same thing over and over. And because we work from the inside out, just like with integration by parts. So that's why I can't stress enough, use technology to check your answers, because it can be really frustrating if you're getting the wrong answer. Did you just forget a negative sign or a 2 or a factor of something? Or is the problem actually set up wrong? So leverage technology when you're going through the homework to check your answer before you go through and do the triple integral by hand, okay? Because guys, that happens to all of us. You guys just saw, I just did a problem and I messed up subtracting the fractions. And that gave me the wrong answer, even though my integral was set up correctly. So that part happens to all of us. And I don't want you to drive yourselves nuts with that. So please, please leverage technology, Wolfram Alpha or Symbolab. Sometimes with triple integral Symbolab's a little easier because we actually put it in math notation. All right. Any other?
Have a nice night.
What's that, Garrett? Sorry.
I said, have a nice night.
Thanks, Garrett. You too. All right, guys. Let's go ahead and end there. Sorry for talking the whole time. Sorry you guys didn't get a chance to work. I'll make sure that Thursday you guys have a little bit more chance to try some of this stuff out. I'll have it all posted tonight. So let's go ahead and end tonight, and I will see you guys on Thursday. As always, guys, you have access to, email, the forum, and tutoring, so take advantage as needed.